Okay, in this video we're going to look at 4 examples of center of mass. First example will be center of mass for discrete particles in one dimension. The next example will be center of mass for discrete particles in 2 dimensions. The third example is going to be dealing with a bent wire, which is 2-dimensional. And then the last one that we look at is going to be dealing with planes or surfaces. And so this would be like a sheet of plywood that has been cut into a particular shape. Now, in each one of these examples, I want you to pause the video and try to calculate the center of mass on your own. This, again, should be review for you, and so test yourself and see how it goes. Okay, so in our first example, pretty straightforward. We have 4 particles, and the center of mass, if we just try to reason this out a little bit, there is no particular symmetry going on here, so we can't just say, aha, this is going to be the point that is where the center mass is located. What we know based on our understanding of center of mass is that for each pairs of particles, we know that the center of mass is going to be located closer to the heavy one, and there's some ratio that it would be, but I don't know what that is off the top of my head. So we're just going to have to go through and do our calculations. The other symmetry that we can see in the grand scheme of things is that the center of mass for the whole system is going to be somewhere located around this 2-kilogram object on the left. These are going to be considered point particles. Part of the reason for that is that we're going to treat them as perfect spheres, and we're outside of the sphere, and so we can treat it like it's a point particle because mathematically that's what it turns into. Okay, so let's start by writing our equation for center of mass. And we have xcm is equal to m1x1 plus m2x2 plus m3x3 plus m4x4 all over m total. And yeah, this is a longer problem than you're used to because we have 4 objects, but I want to make sure that you're really comfortable with center of mass. Okay, so at this point it really is pretty much a plug and chug kind of problem. So for M1 we have 1 kilogram. For X1 we have minus 2 meters. Then we have 2 times 2 plus 1 times 4 plus 2 times 5. And that's all going to be divided by 2 and 2 is 4 plus another 2 is 6. So that's going to be 6 kilograms. All right, so we get a minus 2 plus 4 is going to give us 2. So 2 plus another 4 is 6, and 6 plus 10 is 16 divided by 6. So our location for the center of mass is 16/6, or we'll just go ahead and calculate that for real. And that's going to be 16 divided by 6 is 2.67 meters. So we have 2.67 meters as the location for our center of mass. If we want to mark this on our diagram, right here is going to be 3. So somewhere in here is the location for the center of mass. Now, I want to point out that center of mass is not always, I'm going to just calculate xcm. In these types of one-dimensional problems, it's not uncommon to for example, have a long object, maybe it's like a seesaw sort of arrangement, and you have an object located here, and then an object located here, And of course, our seesaw, it also has a center of mass located at the middle. And what they do is they tell you that this object, this arrangement, balances out at this point right here. And so if this is the point where it balances, then this is going to be xcm. And you would have to then solve your equation here for whatever that missing quantity is. Maybe it's what is this mass here? That's not uncommon. Or what is the location of that mass? And they tell you what that mass is. So just keep that in mind for these simpler cases. We're not typically necessarily just finding what is xcm. Now, in the more advanced stuff that we do, typically that's what we're doing. We're just finding xcm. Okay, so you can see here now in example 2 that we have a two-dimensional scenario with discrete particles. Again, try to conceptualize where the location for the center of mass of these particles are going to be. You can do that one on your own before we go over it together. Keep in mind that these are the masses here, of course, and that this is the ordered pair for the coordinates for the location of the center of mass. Center of mass is going to be located, of course, at the exact center of each one of these. All right, so that's what these ordered pairs are referring to. So go ahead and attempt this problem on your own. Pause the video, and then we're going to go over it together. Okay, so if we want to try to reason out where the center of mass is going to be located, what we know for sure is this 3 kilogram mass is located further down than this 2 kilogram mass. And that's really, if we only looked at these two, that would shift the center of mass to a location which is below the x-axis. However, we do have this 2 kilogram mass, and it's drawn incorrectly here. If you'll notice, it's actually down on the x-axis. And so what that's going to do is that's going to pull our center of mass from maybe like this location here to something which is closer to the x-axis. And then we have this little 1 kilogram mass that's really kind of up there good ways, and that's going to pull the center of mass up even further. So what we're expecting for an answer is that it's going to be somewhere around the x-axis, pretty close to it, and that just by the looks of it, we're going to be shifted to the right of the x-axis just a little bit, because the small mass is to the right. This 2 kilogram mass is also to the right, a distance of 3 meters. And this 2 kilogram mass will more than offset the one that's on the left. And so we should clearly have a center of mass which is somewhere to the right of the origin and somewhere in the vicinity of the x-axis and the y-coordinate. So when solving these problems, we're going to have to work both dimensions independently of each other and then put it all together in the end. And so we have for the x dimension, and again, we're basically looking at a plug and chug. The most confusing part about this whole thing, and it happens to me regularly, as experienced as I am, is that whenever you're looking at your ordered pairs for the coordinates of these masses, you end up switching a y with an x somewhere along the way, and you just calculate it wrong. It's not that you didn't know what you were doing, you just made an error, because that's what humans do, we err. Anyways, we'll just start from the left. This will be M1. We'll make this M2, M3, and then finally M4. We'll just go clockwise through just to be organized about it. And so what we get is M1 is equal to 2 kilograms times a minus 2 meters. All right, so XCM is equal to a minus 4 plus 1 is going to be minus 3. Minus 3 plus 6 will be 3. And then, so that's just going to be 3 divided by 8, or 3/8 of a meter. Okay, so we know that our center of mass is going to be located somewhere along the line that's 3/8. So it's going to be somewhere along this line. All right, now let's take a look at YCM. Now YCM, this is the one that I personally always mess up a little bit, but YCM is going to be equal to all right, so YCM is equal to 4 plus 3 is 7. 7 plus a minus 9 is going to be a minus 2, so it's a minus 2/8, which is equal to minus 1/4 meter. Okay, so our location for the center of mass, so RCM is equal to 3/8 I hat plus or minus 1/4 J hat, and then from there you can figure out what is the magnitude and what is the direction. But basically we have somewhere around here, so this is going to be, at this location right here is our center of mass, and so we have 3/8 comma minus 1/4 as the ordered pair for the location of the center of mass. If you wanted to, you can find the magnitude and direction from the origin. And so all I simply mean with that is that if you wanted to write that as a position vector, you could draw it out as that. Okay, I would like for you to try this third example on your own. You've seen it before, so this is really, again, just a review. There's no new information here. But let's see what you come up with on your own, and then we're going to go over it together. There's a lot of things to discuss, just really big reminders from what we did last year. Okay, so again, our strategy is going to be pretty straightforward, just like before. Each of these segments of wire we're going to treat as uniform, and they're clearly symmetric. So really what's going to happen is we're going to take this object and turn it into 3 discrete particles. And we're going to have at this location here the center of mass for this piece of wire. At this location here, the center of mass for this piece of wire, and then at the midpoint here, we have the center of mass for that piece of wire. Now, we know that because this piece and this piece are uniform and symmetric, they're the same mass, same length, that somewhere along this line right here, we would have the center of mass for these two. But then we have this piece right here, which has a mass that is half that of either one of these segments. And it's located further out, so it's going to pull the center of mass more to the right. And then, of course, because there's no bottom half, it's going to pull the center of mass up. So we would expect the center of mass for this whole wire arrangement to be located somewhere in this upper right quadrant that we have here with that piece of wire. So let's just go ahead and get started with it. This is two-dimensional, so let's fill in some information. For example, we're going to say x, we're just going to put the coordinate system, the origin right here. All right, so that's 0, 0. And this location for this center of mass is just going to be 0, comma, 1/2 L. The location for this center of mass is going to be 1/2 L, comma L, and then the location for this chunk of the center of mass is going to be L, comma 3/4 L. Okay, so this is going to add a little layer of complexity. All right, then now that we have our coordinate pairs, let's set up our equation starting with the x dimension. So we have xcm. And now we get into the part that requires a little bit of discussion. Because what is the mass for any one of these particles? You know, and well, in any one of these wire segments that we're treating as point particles. So M1, again, we're going to go clockwise. We'll say this is mass 1, mass 2, mass 3. So what we know, just by looking at it proportionately, mass 1 and 2 are going to be equal in size, and then mass 3 is going to be half that. But how do we demonstrate that? Well, the way we demonstrate that is going to be using our mass densities. Remember that density that you're most familiar with is volume density, or volume mass density, and we would write that in physics as rho is equal to mass per unit volume. But we can also do it for a wire segment and then a surface, something that's two-dimensional. So this is a three-dimensional density, this is a one-dimensional density, and the next example will be a two-dimensional density. So we have, for a two-dimensional density, we have an area, which we could say the surface, right? Sigma, surface. That's going to be equal to mass per unit area. And then we have lambda is equal to mass per unit length. So for lambda, think line, right? The first letter of spelling out lambda is an L, so lambda line. Surface or sigma, right? So think of this as surface for sigma, and I have no idea why rho and volume go together, but that's what we use in physics, so I go with it. All right, so how do we demonstrate what the mass is going to be? Well, it's simple. We just take this equation here and we solve it for mass. So we know that mass is going to be equal to lambda times L. Okay, so we get xcm is equal to lambda times L times x1, and x1 is 0, so that's times 0, plus m2, so m is going to be equal to lambda times the length, which is L. So we get lambda times L once again. And for the second position, you know, in the x dimension, we have 1/2 L. So this becomes 1/2 L plus m3, which is going to be lambda times, and now the length of this wire is 1/2 of L. So this becomes 1/2 L. And then x3 is just going to be equal to L. And then we divide that by the total of lambda L plus lambda L plus 1/2 lambda L. So we get lambda L plus lambda L plus 1/2 lambda L. All right, so we can start to cancel some of this stuff out. And I think we can see that lambda cancels and L cancels for a lot of this. But be careful, when we cancel, that doesn't just make it disappear, it becomes a 1. Okay, so you know, by making these L's go away, one L from each term go away, we just have the number 1. By making lambda from each term go away, we have the number 1. So this effectively becomes 1 times 1, and a 1 times 1, and a 1/2 times 1 times 1. So we get 1 plus 1 plus 1/2, which is 5 halves. Okay, so that's write that out a little more carefully. XCM is equal to, so there's a lambda in every term. Let's cancel out all of the lambdas. There's one L in every term, so we can cancel out one L from every term. And notice that that's going to leave us with just units of L, or meters, which is what we expect. That's what we need. Okay, so XCM becomes 1/2 L times 1 plus 1/2 L times 1 divided by, and remember this is 5/2, or we could just say 2.5 to keep it simple. And so what we have is 1/2 L plus 1/2 L is L divided by 2.5. Or if you write it out as 5/2, that becomes 2/5 L. Okay, so if my mental math is correct, we have 2/5 L for the x dimension. And that does place our center of mass to the left of this line. So my original reasoning was not exactly accurate. And that makes sense because in the case where this wire on the right was a length of L, we would have the center of mass located along this line of symmetry right here. Okay, so there's a line of symmetry right there, and because the piece on the left is heavier, it actually pulls it to the left. So this actually conceptually does make sense, and so I'm good with that. We're going to keep that as a valid answer. All right, now YCM, we have the same basic process, okay, except now for YCM, okay, so for YCM we have M1, which we know is lambda L, plus M2, which is also, or I'm sorry, M1 times Y1. Y1 is 1/2 L, so we still have to multiply that by 1/2 L. So we get lambda L times 1/2 L, plus lambda L times L, plus 1/2 lambda L times 3/4 L. And we divide all of that by what we know now is going to be 5/2. So finally, we just do our math. YCM is equal to, all right, so remember, this becomes L here, lambda L, I'm sorry. And so remember that we're going to get a lot of stuff here to cancel. Lambdas all cancel. 1 L from each term cancels. And so finally what we have is 1/2 L plus L plus 1/2 times 3/4 is 3/8 L. So that's going to be a little bit ugly. Let's see here. We have 3/2 L plus 3/8 L over 5/2. All right, so here's my mental math again. All right, let's see here. So we have 3/2 is the same thing as 12/8. So 12/8 and 3/8 is going to be 15/8 L over 5/2. So that's going to become 30/8 over 5, or 30 divided by 40, which is 3/4 L. All right, now does that make sense? Well, let's look at that. We have 1/2 L here. Then we're going to pull it up even further by a distance of half this, because this piece is the same mass, so that's 3/4 L. and the center of mass of this one happens to be located along that same line, so this chunk does not shift the center of mass in the y dimension at all. So what we end up with is a coordinate pair where we have the center RCM is equal to 2/5 L, comma, 3/4 L. Okay, so 2/5. All right, so we know it's along this line here, 3/4, and 2/5 is about 0.4, so it's located right about there. That is the center of mass for this system. Okay, lastly, let's take a look very briefly. I don't think I'm going to complete this one in its entirety, but we are going to look at a strategy for solving it, because it's basically like doing the discrete particles in 2 dimensions, just like the last 2 examples. And so when we look at this, the first thing you need to do to be able to break it into discrete particles is ask yourself, how do I section off this shape? And there's no one right way of doing it. I think there's a couple of obvious ways of doing it. One could be to break it here, and the center of mass would be located there, and then there, so you would only have 2 pieces, and that's fine. Some of you may see it as being broken here, and that would be fine as well. And then of course the center of mass for each piece would be this and this respectively. You may just want to break it into 3 pieces, and then you'd have a center of mass here, here, and here. All right, so it's really up to you how you want to do that. You just have to be careful, because this side here is length 1/2 L, which means the center of mass location along this line is going to be 1/4 L if we're using this point here as our origin, the bottom left corner. So that's going to be 1/4 L in the x dimension, and so you might miss that. All right, and then lastly, the mass of each piece. Remember that we said that for volume density, rho is equal to mass divided by volume. And for surface density, we have sigma is equal to mass divided by area. And then finally, for a line, we have lambda is equal to mass divided by length. All right, and so for each one of these pieces, we're looking at area. And so, for example, if I just look at one block, then one block we might say is mass is equal to sigma times A. We know that each one is going to be uniform, so sigma is the same for everything. But proportionately, the area of this block is the same as the area of that block, and the same as that block. But suppose that you had broken it up into 2 unequal pieces. So we have that top piece right here, so proportionately A is going to be equal to 1, and then we have this bottom piece here. Try to get rid of that real quick. All right, so we have this bottom piece here, and we could say that proportionately the area is equal to 2 times the area of that top piece. I mean, that's basically what's happening. All right, so if that's the case, then what we have is for that bottom piece, the mass is equal to sigma times 2a. And then, of course, somewhere along the way, the a's are going to cancel and the sigmas are going to cancel, leaving you with just what we need to solve it.